1000, that is where the Flamington number is. Okay? And how did we define the Reynolds number? It is the density times the speed. Okay, not the velocity, the speed. Okay? Times the size divided by the dynamic viscosity, and if I divide the dynamic viscosity by the density, I get something known as the kinematic viscosity. Just figure out the SI units, okay? Oops. Look at this problem. So consider two situations, and again please pull out your calculator. So I'm giving you two situations. An insect measuring 1 point. You might have seen these little insects, floating in your pond, okay, or doing these little motions. A 1.5 centimeter insect swimming at a speed of 5 times its own length per second in pure ethanol. Okay, instead of water, I'm giving it ethanol at 25 degrees. I've given you the ethanol density in CGS units, 0.789 gram per cc, 789 kg per meter cube, right? And I have given you the viscosity as 1.1 centipoise. Okay? So, what I need to do is not write without touching. The conversion of poise to the corresponding SI units. What are the SI units? Pascal second, right? So 1 poise is 0.1 Pascal second. Huh? So just make it 1.1 into 10 to the power minus 3 Pascal second. Okay? So it is actually more viscous. Ethanol is more viscous than water, but it has lower density than water. Okay? So if I do this, alright, so water, I'll just give you viscosity of water is 1 centipoise. Okay, so it is 10 to the power minus 3 pascals. So it's a unique situation, This alcohol is 10% more viscous than water. At the same time, it's less dense. So you have to get down to the molecular properties. But if I look at situation A and situation B, can you give me, can you give me in A, what is the Reynolds number? How much? 807, right? So I'm going to write it as 0.8 into 10 to the power 3. 800. Remember, 1000 is when I said you will make a critical transition. And in the second case, what is the Reynolds number? It is a really, really small number, right? So I'm talking of nearly 4 orders of magnitude difference in the Reynolds number. So although in the first case we are below 1000, okay, but compared to that situation we are much more turbulent. Okay, so use your imagination a little bit and think of a insect moving in water versus a microorganism. Look, ethanol and water, they are viscosity more, density less, but they are not orders of magnitude different. Okay, so whenever you have this little microorganism, trying to, for you, water is turbulent. When you go swim, obviously it's turbulent, but for a microorganism, it is actually a very laminar flow. So what are the consequences of that? That is something that, we can think about. So how do they manage? Okay, so this is a slight diversion. We will do this a little bit subjectively. Microscopic organisms have flagella or cilia. Cilia is more present in other, cilia is there. I'm not going into the details. I'm not an expert on where cilia is present and where flagella is present. But bacteria have flagella and the inner structures of flagella and cilia are very different. Okay, but at the end of the day, both are actually creating local turbulence. Okay, you are expending a little bit of energy to create that local turbulence. And what is the benefit of creating local turbulence? Anybody? Not clear.
The water pushes you back.
Water pushes you back, that wouldn't help. It's actually very simple. If you have turbulent motion, you can perhaps get more of the nutrients that are dissolved.
But it is as equally likely that you are pushing away nutrients. It is equally likely that you will end
But
up.
you're depleting. If you're just waiting for diffusive movement of your nutrient molecules to come to you, the time via which you will get your nutrients, time scales are much longer. But if you create turbulence, you're going to actually get your nutrients faster.
No, but it is equally likely that you end up pushing away the nutrients. Depends on that.
That's you can argue that. You can design a setup where you supply it originally with a uniform nutrient distribution and check, right? But biology has evolved to have these kind of things. Okay, so we have just a diagram showing flagella and cilia. Both create local turbulence. Okay. There's there's no way we are going to derive any of this, but let us focus. I just want to tell you just a 2-minute story about this. Flagella, as you know, you have flagella on E. coli surfaces and all that, right? And those of you who have studied mechanics a little bit, know about they talk about engines. These crank engines, crankshafts and things like that. There's no way I'm an expert. But it turns out, to make a really, really long story short, flagella has exactly the same mechanics as a crankshaft. Okay? Though it's a biological entity, the inner structure of the flagella is such that it can, make these sudden jerky movements, okay, on very tiny scales. So essentially what happens is, that force is proportional A times V by, divided by, when you have a viscous fluid. You can actually show that, it is proportional to some constant, I won't bother about it, but there is going to be the viscous friction coefficient that will show up again. We have been introduced to this guy quite a bit. And what fluid dynamics shows you that, depending on the direction of your motion, your zeta, your viscous friction coefficient is going to be a variable. So it is not uniform depending on, it is not uniform this way and this way. Okay, so we have zeta perpendicular, zeta parallel. What do I mean when I say zeta perpendicular? This is perpendicular to the direction of motion and this is parallel to the direction of motion. Can you imagine that? If I'm going this way, okay, the direction in which I'm going, my frictional coefficient is lesser and I'm facing more because my surface is more and so on and so forth. I'm not going into those details, okay? This is also discussed very qualitatively in your biophysics textbooks. I'm just telling you these so that you can take it further if you want. The consequence of this is that the actual resistive force in this direction and this direction, they're not the same. And also it can be shown that your, the net movement, if I have V parallel here, V perpendicular here, the net movement, which is the vector sum of this direction and this direction, is actually not, say I have put unit vectors in this formula. Your net movement and the net force, they are not exactly parallel. Okay, again, you can, so force direction is closer to the normal and your flagella is actually using this physics to work it out. So the velocity components, except those in the axial direction, can be shown to be cancelled out. So the result of this is there's a net propulsion in this direction by this crank movement. Okay, I made a really long story very short, I know. But this is again very much a physics idea. Okay, you're welcome to read up, but the net propulsion of this is you can actually, the bacteria can operate crankshaft kind of a thing. And now actually we have high resolution cryo-EM images of what the flagella, the place at which the flagella actually hinges onto the surface. Okay, so we have those details. This is not something we would, but just for the sake of completion, I wanted to tell you this. Another consequence. We all know about blood vessels, and chances are, beyond a certain age, we are always careful about what we eat. We want to keep our arteries and everything healthy, so on and so forth. Again, without a detailed derivation here, I'm just going to tell you, just imagine this as a very short piece of your blood vessel drawn as a cylinder. Okay? And you know that we have a blood pressure, right? If I were to take a very tiny segment of my blood vessel, I can assume that it's a perfect cylinder. And I'm going to have a pressure difference between the two ends. Okay? And I'm going to call it delta P. That is the pressure difference between, say, the bottom end to the high end, and that is flowing that way. You can show that the velocity of blood, the speed of blood, okay, though we have used V of R, is not uniform throughout this motion if the flow is laminar. Okay? Blood flow must be laminar. Okay? You cannot have turbulent blood flow, then you will not function. Yes?
Is the difference between inner wall or outer wall or up and down?
No, up and down. Okay, so you can imagine that the blood is flowing this way. Okay, so this is one end of your, say, blood vessel, the other end of your blood vessel. See, this flow is given. Okay, and this is the pressure difference. That is we usually measure blood pressure in millimeters of mercury, right? You go and they will put this. So it can be shown that the velocity, that the speed is a function of how far away you are from the axis. Okay, just a second, this will be clear. Oops. So it depends on how far away you are from your axis. So this is your axis. And the speed as a function of axis is a function of delta P, L, the length that we are talking about, the length of, this is L, it's marked, and your viscosity. So now go ahead. What are the factors that I can change? Of course, I can change L and delta P. You can have a thicker artery, you can have a thinner artery, and your blood can be thinner or thicker. You can alter its viscosity by, your drugs and whatever you have. Yeah? Alright. Again, we have not derived it. So, let us actually consider this, and if we have this situation, there are, where is the flow fastest?
At the center.
At the axis. Right? And at R equal to capital R, the flow should be 0, right? And you can see that R square business. So if I want to draw a velocity profile, I think you don't probably need my help. If I have R and V of R, what should it look like? You have a parabola-like behavior, right? This is R equal to 0. Okay. So now with that done, let us look at a problem. Okay, human blood is 3.2 times more viscous as water. Okay, remember water's viscosity is 1 centipoise. So you can think of centipoise is scaled as per the viscosity of water at room temperature. Okay, blood is 3.2 times more viscous. Consider your blood vessel of 2 centimeters, radius 1 millimeter, systolic blood pressure of 120 millimeter of mercury, calculate Vmax. Straightforward. Just do the unit conversion, plug it in. Okay? This one, what I'm going to do is pressure is 120 mm by 760 into 1 atmosphere, right? 1 atmosphere is roughly 0.1 megapascals, right? So, (120 by 760 into, just put in the numbers into, I think, 1.01 into 10 to the power 5 pascals. So I'm in the SI unit regime. I'm doing good. Okay. So how much does this come to? At least by my calculation, this could be 1.6 into 10 to the power 4 pascals. Okay. And my eta is 3.2 into 10 to the power what? Minus 3 pascal second, right? And R equal to 10 to the power minus 3 . So if you plug it all in, what is the Vmax? Figure it out in units of meter per second. I'll leave that as a prompt. Okay? Now you can put it in context. Do some writing. I think just pressing the yes. Thank you very much. Okay? And at the periphery, just near your, where it's touching the blood vessels, you can, the blood is not flowing. Okay? And that is how the nature of the blood flow is. Now, of course, I can thin down my eta by a little bit. Okay? I can increase the blood pressure by a little bit. Okay? So if I want to, keep the same speed and I increase my blood pressure, I will have to, counteract it with a little bit of altered viscosity, right? Such that my flow rate, my speed of the blood doesn't change. So that's a no-brainer, but I think we have not thought about it like that. Okay, another consequence. Of course, there's speed, but a more important physiological quantity is per unit time how much blood is crossing. What is the volume per unit time which is crossing over? Volume per second, that is the flow rate. And that you can get very easily. My flow rate will be, if you 2 pi r dr, you can think of this little thing here, times the velocity. Okay, and I'm sure you can all integrate it, right? So this is simply going to be something like 2 pi 4 L eta by 0 to r. Delta P actually is a constant, r square minus r square times r dr. Running out of space. Do this integration. Okay? If you do that integration, you're going to end up with, fairly well-known formula known as the Hagen-Poiseuille's formula. Okay, it's a general formula for fluid flow. And it does have consequences when you're trying to flow some biomaterial through a tube-like construct. Okay. Now, what are the two things you notice in the first formula and this one? This is an R square dependence. Okay. And here we have an R to the power 4 dependence. Alright? So if I were to, decrease my, so let's do a problem where, R prime, so let's say I decrease my blood vessel radius by 5%. Yes.
Capital R means it is capital R is constant, that is the radius of the tube.
That's a good point because here I'm integrating it. The velocity had a distance profile. But in this case, I'm integrating over R equal to 0 to R equal to R.
So small, it will be smaller.
Huh?
It will be smaller. If you are
No. I'm integrating between the limits of R equal to 0 to R equal to 4. Let me just feel free to talk to your neighbor. Do this integration and let me know if you're getting caught.
Before you said here R square and parabola because
Yeah.
here R shows this is now because R is constant. Before smaller is a variable, so we plotted the velocity. Here, if you plot that, it is just a constant.
Yes, it will be a constant.
There will be no difference.
No. That's not what I mean. So one thing you are right is if I were to, say I'm considering different arteries, small, big, very big. Okay? So R1, R2, whatever, R3, so on and so forth. So if I were to plot R and Q as a function of R, it's going to have, it's going to steep up very much. Okay. But the context over there was a different case. For a fixed capital R, you were noticing that the speed is not uniform throughout this cross section. Clear? It was fastest at the axis and near the blood vessels it was 0. Okay, this is consistent with laminar flow. You might say that I'm making a circular argument, but I'm assuming it's laminar flow, and based on that assumption you can come to this derivation. We have skipped a lot of the derivations here. We are just borrowing from fluid mechanics, yes, but this has important consequences. If you are trying to design a micropipette, or nowadays people talk of these microfluid systems, so on and so forth, right? So these are things you have to keep in mind. But the point is, let's say I have one situation where my blood vessel shrinks, let's say. Okay, this is a situation we are all afraid of, After a certain age, if you're not eating right, chances are all these things might deposit in your blood vessels, right? So let us say that my blood vessel, reduces, the radius reduces by 5%, okay? So say R prime is just 0.95 R. So how much is Q? Because of this very sharp dependence on R, this one, how much is my Q? So Q prime will be how much? So you're losing 19% of your blood. That is, you're reducing your blood flow by a very significant amount, by a very slight reduction in the diameter of your blood vessel. Okay, so that obviously has a lot of consequences. Again, if I were to offset that, okay, so Q prime turns out to be approximately I think 0.81 Q. Okay, so 19% reduction. And of course, you can think that, if I want to, you cannot thin your blood beyond a certain limit, of course, right? I cannot, really water down my blood, right? That won't work physiologically. But what is the limit till what limit can you push this such that you kind of maintain the flow? You might have people in your family who take these blood thinners, right? That is in part to offset these effects. Okay. So this is the kind of, this is just to give you a little bit of a flavor in terms of, we'll do one more problem which I did not pick up today, is going back to, we did talk about it here. So there was this, when we were doing this, we discussed, why is local turbulence necessary? Why is local turbulence necessary? So, if I don't do anything, I'm just waiting for my nutrients to flow to me diffusively, right? So, there's going to be some time. And how will you determine the time for my nutrients to come from one end to the other? If I know the dimensionality, if I know the diffusion coefficient, the time taken would be, for a distance squared, would be
6
r squared by, assuming three-dimensional, 6 times
d equal to
6 times diffusion coefficient, right? But if my water is, or whatever it is, I have created local turbulence, it's no longer laminar, then I can break that limit. Very simply said, you're doing work. Diffusion happens in equilibrium. Okay, we are breaking the equilibrium limit. So now you can create, you are investing some energy to actually get more nutrients. That is how, nature evolves such that there's an advantage to it. To crank that shaft, your bacteria has to do some work, that it has to expend its ATP and all that. So those calculations are very fine calculations. At the end of the day, it is not senselessly cranking the shaft. It's not senselessly expending energy to get something. So there are all these research efforts to understand what is the advantage, how much energy does a bacteria have to invest in order to get nutrients. So you can have a very fine set of equations, set up very carefully. You can create models, you can actually do experiments and, set these things up. I kept that problem aside. We have one more problem again. I didn't get a chance to pick up, but I'll probably, it's okay. Maybe I'll just show it to you on Saturday. Where, if I have a steady state, there have been questions on steady state and equilibrium, right? So imagine you are a bacteria, okay? But wherever you are, there's a steady state amount of sugar solution, say. Okay, it's being supplied, and because you live in a beaker which has a radius of, say, 6 centimeters, and your size is, say, 10 microns. So from your perspective, there's unlimited amount of sugar available just beyond at your surface, right? But as soon as you come to that surface, whatever sugar is there is immediately being taken away by the bacteria. It's being used up, right? In that scenario, what is the limit? What is the metabolic limit that the bacteria can afford to have? There are these little questions that you can actually start thinking about, and you can model these ideas. Okay, but to get to that point, you will have to be very comfortable with whatever we have been discussing in this basic class. and of course you have to read up more on the literature and things like that. Okay. So actually, this evening I didn't make it very long. That's all that I have to discuss. I know everybody is tired and they all look tired. Even I'm tired. But we'll meet on Saturday. Okay. This Saturday, 11 o'clock, same room. Any other questions? We have time, so if there's some confusion that I can help to clear out, feel free to ask now. Okay, you can ask in the class, or if you want to leave and there are people who want to stay back for a discussion, that is fine as well.